All right. Welcome, everybody, to today's String Fino seminar series. We are very happy to have Yuta Hamada from CAG. He will be talking about finiteness and the Swampland. Please go ahead.
Okay, thanks for introductions. First of all, I'd like to thank the organizer for kind invitation to this nice seminar series. So today I'd like to talk about the relation between the finiteness and the Swampland, mainly based on these papers. So, okay. By the way, I was at the Harvard until the end of the March, and from the April, I have moved to KK at Tsukuba, Japan. So let me start from the introductions. Okay, one of the remarkable things of the gravitational theory is the existence of the black hole. So this is a huge difference between the theories with gravities and the theories without gravities. The black hole state is, of course, a highly UV state in the sense that the energy of the state is much bigger than the Planck scale. On the other hand, interestingly, this black hole state can be described within the IR effective field theory, so namely the general relativities. And moreover, somehow the number of the degrees of freedom of this UV state, number of the degrees of freedom of the black hole state can be counted just from the IR effective field theory, as known as Bekenstein-Hawking entropies. So in this sense, even the black hole is a highly UV state, and the information of the highly UV state can be computed from the IR theory. So this exhibits the example of the UV-IR mixings. So this is a non-trivial feature of the gravitational theory, and this is one reason why we expect a Swampland band, why we expect some non-trivial quantum gravity constraints on the IR physics. So in this talk, I try to argue that many of the Swampland conditions are viewed as a prism of the finiteness of the black hole entropies. So in other words, I try to unify the various Swampland conditions in terms of the finiteness. So formally, at least formally, we can build various Swampland conditions as some kind of the finiteness conditions. So many Swampland conditions somehow emerge from suitable replacement of infinity by a finite number, which is a Planck scale. For example, we have the weak gravity conjectures. This roughly says that the gauge coupling is equal or bigger than the mass of m Planck. And when the Planck mass is infinities, right-hand side is 0, so the constraint is trivial. But if we replace the infinities by the finite Planck scale, there is a non-trivial constraint. Similarly, we have the distance conjectures, which roughly says that the displacement of the field range is upper bounded, which is order of the Planck scale times some log corrections. So in this case, situation is similar. If Planck scale is infinity, the constraint is trivial, but as for the finite Planck mass, we have the non-trivial constraint. And we also have the conjectures of the finiteness vacua and finiteness of the Branes moduli and the species bound and so on. So as the name suggests, these are, of course, built as a finiteness conditions, and the species bound can be also built as a finiteness conditions on the number of the light particles. So in this sense, it seems that many Swampland conditions are built as a finiteness condition. So maybe the finiteness is a keyword to unify the various Swampland conditions. So this is a plan of talk. So I try to consider these three topics in my talk. One is a compact Branes moduli and distance conjectures and the finiteness of the vacuas. So let me start from the first part. So, I first talk about the compactness of the Branes moduli. So by using the finiteness of the black hole entropy, we can claim that the Branes moduli space must be compact. So for example, take the some higher dimensional supergravity theory and take the BBF defect in the theories. For example, if we consider the gauge instanton type profile, it is a codimension 4 defect. So it is a D-5 Branes, and on this Branes, the theory, which is D-4 dimensional field theory, lives on it. And if we consider the monopole type configurations, it is a codimension 3 defect. So it is a D-4 Branes and D-3 dimensional field theory living on it. And these Branes have the internal degrees of freedom parameterized by the wave of the moduli. So now I claim that the moduli space of this Brane must be compact because of the finiteness of the black hole entropies. So how can we argue that? We can argue that in the following ways. First, we compactify the theory on torus, D-4 dimensional torus for the gauge instanton configuration and D-4 dimensional torus for the monopole type configurations. Then if I start from the D-dimensional theory on T-5, we have the 5-dimensional theories. And in this case, we have the 4-dimensional theory with 0 Branes. And this 0 Brane is described by the quantum mechanical Hamiltonians. And the quantum mechanical state is described as a wave function of the modular field phi. And if the modular space is non-compact, the quantum mechanical degrees of freedom phi is non-compact, which means that there are infinitely many states for given energy range. So this is shown schematically in this figure. Horizontal axis is phi and vertical axis is a wave function of the phi. If the phi is non-compact, we can consider the, for example, wave packet, which is located at phi equal phi 1 and the width is at del phi. And similarly, I can consider the wave packet with centered at phi equal phi 2 and phi equal phi 3 and so on. And these wave packets are almost orthogonal and almost has the same energy eigenstate. So this means that there are infinitely many states for given energies. So this clearly violates the Bekenstein entropy bound. This entropy bound says that for fixed energy, there is a finite number of the degrees of freedom. So this is the argument. But one may wonder why this is interesting. So one interesting thing is that the compact Coulomb branch or compact modular space can be viewed as an internal geometry of the string theories. Actually, by doing the explicit analysis, we can see that the following correspondence in the case of the 9-dimensional theories, and by considering the modular space of the gauge instantons, the modular space is equal to the modular internal geometry of the type 2A on S multitude. And similarly, in 8-dimensional case, we can find that the compact Coulomb branch is elliptic K3, which is nothing but the internal geometry of the X-theory compactifications. And in 70 case, we can find similar things. In this case, we find K3s, which is internal geometry of the M-theory compactifications. So the finiteness of the black hole entropy is connected to the finiteness of Planck mass in the string theory compactifications. So in the string theory compactifications, finite Planck mass means the finiteness of the internal volume. And this corresponds to the finite black hole entropy in our argument. And moreover, the consistency condition of this internal geometry gives rise to strong restrictions on the possible patterns of the gauge group. So this is one very interesting consequence of the compactness of the Branes modulus. So if you are interested in the detail, please look at these papers. Okay, so far I tried to argue that the Branes moduli must be compact. And another interesting direction is following. If we could apply this argument to the space-time filling branes, which have the compact moduli, this means that the bulk scalar field should be morally compact. So if this is the case, this can be connected to the distance conjectures. So because the distance conjecture says in some sense, every scalar field is compact for fixed cutoff scale. So I want to go to the topic of the distance conjectures and try to connect the distance conjecture to the finiteness. So maybe all of you know about the distance conjecture, so I briefly say about it. So distance conjecture says that if I move the infinite distance in the moduli space, tau of the state becomes light, exponential becomes light, like this. So in other words, EFT cutoff scale scales exponentially small for the at a large distance. So there are plenty of the evidences from string theories. So distance conjecture is tested by the, for example, the compactation with 8 number of the supersymmetry or more supersymmetry, or theories with 4 supersymmetries. So these are the incomplete list of the references. So there are plenty of the evidence from the string theory compactifications. On the other hand, so far main support comes from the examples in string theory. So what we are trying to do is to try to give the explanation or try to motivate the distance conjecture from the bottom-up perspective without using the string theories. Okay, what we are trying to do is the following. So first we take the d-dimensional free scalar theory without potential. Then we compactified theory to the 1 dimensions. So if I do that, this is the Lagrangian of the d-dimensional theories, and if I compactify it to 1 dimensions, the system becomes quantum mechanics. So the Hamiltonian is just been by the free particle ones. And then I impose the finiteness of the partition functions. So I will briefly discuss later, but the finiteness of the partition function may be built as a natural generalization of the finiteness of the black hole entropies. In any case, if I require as a finiteness of the partition functions, then this scalar field must be compact scalars. Otherwise, we have the infinite number of the continuous states for fixed energy range, and the partition function diverges. So the way to avoid this infinite divergence is to compactify the scalar. So in other words, I introduce the periodicity of the phi, which I denoted by the phi max. Then the partition function is finite, manifestly finite, and is written like this. Then if I try to obtain the effectively non-compact scalar, which means that if I try to take the limit where the phi max is infinities, I get these expressions. So of course, this is divergent naively. So in order to keep the partition function finite, I also take the cutoff scale to be 0 at phi max to infinities. concretely, the finiteness of the partition function requires that cutoff scale scales like this. Lambda is below the 1/5 max squared. So I claim that this is a weaker version of the distance conjectures. Namely, the cutoff scale cannot be constant. Cutoff scale must be 0 if I take the limit phi max to infinities. But this is a weak one because cutoff scale scaled as a power law, not exponential mode. But in any case, I think it is interesting that at least we can argue that cutoff scale must be 0 for the infinite field range. Okay, one of the interesting things is that this is a nice connection to the emergence proposal and proposed in these papers. The emergence proposal is infinite distance is a IR emergent concept, which is absent in the full theory or UV theories. So the rough argument goes as follows. So we consider the tower of state, which are denoted by a psi n, and the mass of the psi n is mn squared. And I assume that this is the tower of the particle parameterized by these functions. And by integrating out the tower of the particle, this gives rise a correction to the field space metric of phi. And just by computing the one-loop Feynman diagram, I obtained these expressions where the n is the number of the state below the species scale. Then this leads to the following expressions. And when this one-loop correction dominates, then it says that mass of the tower is nothing but the exponential minus del phi. So this is a behavior of the distance conjectures. So this is a quite nice argument. But one question to this is that why not infinite distance from the beginning? What is wrong with that? So we provide the answer to that. It is because finiteness requires UV compactness. So we cannot have the infinite distance from the beginning. It must be emergent. Okay, let me go back to our requirement. I required that the partition function is finite, but why? So one thing I want to say is that Bekenstein-Hawking entropy is obtained from the gravitational partition functions. So in this sense, that finiteness of the black hole entropy means finiteness of the partition functions. So, and we believe that this requirement, finiteness of the partition function, would be the consequence of the more fundamental requirement. And we propose that this is a consequence of the amplitude of quantum gravity is finite. So because if there are infinite number of the state for given energies, so there is so each state contributes to the amplitude, which tend to diverge the quantum gravity amplitude. So we do not have the Liouville connection between them, but we believe that the fundamental concept will be the finiteness of the quantum gravity amplitude. Okay, there are two related comments about the distance conjectures. So far, we consider the case with vanishing potential, but we can do the same argument with potential as long as the potential goes to constant at phi to infinities. So we have the same bound. The cutoff scale is smaller than some power laws. Moreover, assuming that there is a tower of state which becomes light, this V0 cannot be positive since it violates a Higuchi bound, which is a unitarity bound for the massive spin part, higher spin particle in digital space. So Hubble scale is smaller than the mass of the towers, but we assume that the mass of the tower becomes 0 for the phi to infinity. So H cannot be positive.
You have 5 minutes before questions.
Oh, okay. Okay. So I have to write. Okay, another comment is that we can argue that magnetic wave gravity conjecture from the entropy bound in this specific type of the theory, Einstein-Maxwell-Diraton theories. And assuming the behavior of the gauge couplings, there exists small black hole solutions. By small black hole solution, I mean that it is horizon less or size of the horizon 0 at the leading order. So if there are actually there are infinite number of the small black hole solution naively, and this can be built as a particle state. And if we consider the box with size L and entropy bound, there are too many small black hole states, which violates entropy bound. A way to avoid it is to impose the cutoff scale is below the gauge coupling times the Planck scale. So if this is the case, only a finite number of the small black hole solution is trustable, and this trouble is avoided. And this is nothing but magnetic wave gravity conjecture. Okay, finally, I want to go to the finiteness of the vacua. So we propose the following. The number of the low energy EFTs after quotient by the modular space consistent with the quantum gravity that are varied up to the energy scale cutoff lambda is finite. So this conjecture again built as a finiteness of the quantum gravity amplitude or finiteness of the quantum gravity partition functions. Because if there are the infinitely many vacua, we will get divergent amplitude of the quantum gravity. If we compactify the theory to the low enough dimensions, and if there is a contribution from each vacuas, so if there are infinitely many vacua, we will get divergent amplitude. But if we naively, it looks that there are infinitely many vacua in the quantum gravities. For example, there's a famous example, the ADS 5 times S5 vacua, and naively infinitely many vacua exist with infinitely many choice of the flux quantities. But this does not contradict to our proposal because, okay, this is the potential of the these compactifications, and this is radius, horizontal axis radius, and smaller radius is dominated by the positive contribution from the flux, and large radius is dominated by the negative contribution from the curvatures. And there's a minima, which I denoted by R stars. And if I increase flux quantas, then R star increases. And therefore, for fixed lambda, only finite numbers of the flux quantum number is allowed, because otherwise the KK mode becomes lighter than the cutoff scale. So this is consistent with the proposal. So another support is a Chiga theorem discussed in this paper. So this is a mathematical theorem which states that finite numbers of diffeomorphism types of the Riemannian manifold with bounded curvatures, volume, and diameters. So this is a condition where the classical supergravity approximation is trusted. So this theorem is that in this class of the situations, there's only finite number of the topology class. And similarly, there's arguments that for fixed Calabi-Yau, there is only finite number of the self-dual flux vacuas. So this is again the support of the conjectures. Okay, so let me summarize my talk. So I have argued that many Swampland conditions are built as a prism of the finiteness of the black hole entropies. Specifically, I argue that the finiteness is connected to the compactness of the Branes moduli and the distance conjectures and the finiteness of the vacua. So this is the end of my talk. Thank you very much.
All right. Thank you very much, Yuta, for your very nice talk. Are there questions? Well, people are thinking, oh, sorry, yes. Go ahead, Arthur.
Sorry, I have my view somehow not well. Okay. I have a very naive question. Sorry, it was a very nice talk. I enjoyed very much, but I have not understood the details of the finiteness statement in quantum mechanics.
Okay. Okay.
Because, for example, if I compactify just on S1 or on a product of 9 S1s, I get, of course, a quantum mechanical model with a parameter, which is a radius of the S1, which is simply infinite, obviously infinite, right? And the partition function of that model is not finite. And I assume you will somehow argue that you need to impose a cutoff. But what exactly is a cutoff in quantum mechanics? Is it somehow the mass gap to the lightest excitation, or how do you argue against the example of compactifying simply with full SUSY on S1s?
Sorry, what the situation you could say? You start from
I compactify on an S1, and the radius of the S1 is a modulus, which is manifestly non-compact.
Sorry, you
have a quantum mechanical model.
It's S1 times T9 or something like that?
Yes, T9, for example.
Okay, okay.
It's clear the partition function is not finite. You need to impose something more.
Yeah, it is not finite. So I mean this is I think it is our statement. Partition function is not finite. It is divergent. So there must be something.
Yeah, but it's a trivial example. I mean, you must somehow have a what exactly is the condition? So if your general statement is partition function has to be finite.
Yes.
And this is the counterexample, and you need to say something about this counterexample, I think. How do you exclude that? How do you formulate your theorem or your conjecture more precisely such that this counterexample is killed?
I'm not sure if it is a counterexample because to compute the it's a. I mean, if okay, you have the moduli of the S1s, and partition function is finite if I trust that moduli has an infinite field range. So if it is non-compact, it is divergent, but it cannot be.
It cannot be. I don't understand.
Cannot be because so I just try to say that if I consider the moduli space of the S1 radius, we cannot use the same effective theories for the S1 is small and S1 is large. So we have to go to another effective field theory to compute the partition function correctly.
I think nothing is wrong if I go with the radius to infinity. I think what you need to say is that you somehow introduce a cutoff in your quantum mechanical model. I mean, I think the statement partition function is finite, it's just too strong. But then formulating a cutoff in quantum mechanics is not. But that's not trivial because if you formulate how do you formulate what a cutoff is in quantum mechanics? That's my question. Technically, how do you exactly make your statement?
Do it as a cutoff.
You could say, one suggestion would be that you say that the lowest excited state should be a finite distance away from the vacuum. Right? Similar to TK's game. But that is problematic. If you say that, then somehow isn't the partition function then no. So I guess something like that must be the answer. Yeah, maybe the partition function then automatically finite if you do that, right? If you have a.
Yeah, I'm sorry that I have to think about that example carefully, but I think I basically agree with that. We have to introduce a cutoff, and we
in quantum mechanics.
In quantum mechanics.
Okay. Thank you.
Thank you for commenting.
All right. In the interest of time, we have to move on. So thank you very much again, Yuta.